Hey there. Today we're going to talk about the power series. Now, this is actually a power series for e to the x. So you can say that e to the x is approximately 1 plus x squared over 2 factorial plus x cubed over 3 factorial, and so on, where the nth term is x to the n over n factorial. Now, if you allow that to continue out infinitely, then that's actually the exact value of e to the x. But up here, since I stopped it at a particular value, that's only the approximation of e to the x. So by definition, a power series is defined down here to be, it's basically a series where you're summing a series a sub n times x to the n, where n goes from some number to infinity. Now here we're saying 0 to infinity, but it doesn't have to be 0 every time. So if n is 0, then the first term would be a naught, which is the a naught, and then if n is 1, you would get a1 times x to the first. And then if n is 2, you would get a2 times x squared, and so forth. a3 times x cubed for n equal 3, and then the nth term would be a sub n x to the n. This is a power series. Now, if we replace x with x minus a constant, then in that case, we would say we're centering the power series about that constant. So up here, the power series is centered about 0. But down here, this is how the power series would look if we centered it about the constant c. So again, it would look very much the same. You would just replace x with x minus c, but you would get a naught plus a1 times x minus c to the first power plus a2 times x minus c squared, and so on. And so the nth term would be a sub n times x minus c to the n. Here's a couple of power series centered around 0. So if you'll notice, these two, they both go, this one goes from 0 to infinity, and then you have x to the n, and actually the a sub n part is 1 over n plus 1 quantity squared. So that's the a sub n, 1 over n plus 1 quantity squared. Now here you have x to the n, and the actual series that goes with it is negative 1 to the n over n. So that would be the a sub n. Okay, so I'll let you plug values of n in, and you can see if you plug 0 in for n, you just get 1. If you plug 1 in for n, you'll get 1/4 x. If you plug 2 in for n, you'll get 1/9 x squared, and so forth. So you can do that as a little exercise. And the same thing here. This one, I'm going to go from n equal 1 to infinity because it wouldn't make sense to go from 0 since you'd be dividing by 0. So we're going to write this from 1 to infinity. So if you plug n equal 1 here, you would get minus x, and for n equal 2, you would get 1/2 x squared. For n equal 3, you would get minus 1/3 times x cubed, and so forth. And so that would be centered about 0. Now, if you wanted to center a series about 1, then instead of x to the n, you would have x minus 1 to the n. So here my series 2 to the n is paired with x minus 1 to the n to create a power series. And so then if you let n be 0, you'll just get 1. If you let n be 1, you'll get 2 times x minus 1 to the first. And then if you let n equal 2, 2 squared is 4, so you get 4 times x minus 1 squared. And if n is 3, you'll get 8 times x minus 1 cubed, and so forth. And then here's another one, another example of an alternating series. And again, this series, the a sub n is negative 1 to the n over n factorial. And then the power series portion would be the x plus 2 to the n. So if you let n equal 0, you'll just get 1. If you let n equal 1, plug 1 everywhere there's an n, and you'll just get minus the quantity x plus 2. And then if you have n equal 2, you'll get 1/2 x plus 2 quantity squared, and so forth. And notice that this is centered about -2, so when you subtract -2 you actually get x plus 2 in the power series. Now a power series does not generally converge for all values, so it depends on what we find out about these series. So for a power series that's centered at C, only one of the following three things can happen. Okay, so either the series converges only at the value C, or there exists some number R, positive number R, such that the series converges absolutely for all absolute values of x minus c that's less than R, and then it diverges for all absolute values of x minus c greater than R, or the series converges absolutely for all values of x. Now, in this case, the interval of convergence would actually be between x would fall between c would fall between what did I say in here? X falls between c plus r and c minus r. Here, if it converges absolutely for all x, the interval of convergence would be minus infinity to infinity, and then here the interval of convergence would just be a single number. Now the radius of convergence is the distance from R. So if the series converges only at C, then the radius of convergence is 0, and if the series converges for all x, the radius of convergence is infinity. And the set of all values for which the power series converges is called the interval of convergence. So to test a power series for its interval of convergence, what you do is you take the absolute value of x minus a here and set it less than r, and then that way you'll know that x is between a minus r and a plus r. Actually, a here is the same as c, so didn't mean to confuse you there. Now, if the interval of absolute convergence is finite, we test for convergence or divergence at each endpoint using one of these three tests. If the interval of absolute convergence falls between two values, the series diverges. It does not even converge conditionally because the nth term does not approach 0 for those values of x. So, in other words, if the interval of convergence is between these two numbers here, then the series diverges. So let me reiterate what I said here. If the interval of absolute convergence is this interval, then the series would diverge. It would diverge for values outside of that interval. So therefore that's what that's telling you there. Okay, so now let me just do an example and I think you'll understand here. Okay, so if I wanted to find the interval and radius of convergence for this series, I would do the ratio test. So I would take the absolute value of x to the n plus 1 divided by x to the n, and if you divide x to the n into x to the n plus 1, you just get x. So that would be the limit of the absolute value of x. And so since x doesn't depend on n, then this would just equal the absolute value of x. So now what we do is we set that result less than 1 because that's how we find the interval of convergence. So if you solve this inequality, you'll find that x falls between -1 and 1. So that means that this series converges on that interval. Now, what about at the endpoints, -1 and 1? Well, we'll test these individually. If x equals -1, then plug -1 in for x, and you just get this series, which is -1 to the n. Now, if you tried to add this up, you'd get 1 plus -1 plus 1 plus -1, and so the sums would alternate between 1 and 0. So it actually would never converge to a particular value, so therefore it diverges at -1. Now at x equal 1, you get the series 1 to the n, and that series actually that sum would actually increase without bounds, so therefore it diverges. So it doesn't converge at the endpoints, so we would write the interval of convergence as -1 to 1, and then the radius of convergence would be 1, because you'll notice that each one of these numbers is 1 unit from the center, which is 0. And you can do this practice problem and show the same thing. Just remember, when you take the absolute value, when you have this -1 to the n, the -1 to the n disappears because the absolute value of -1 is 1. Okay, so let's do the next one here. Here I have the series x to the n over n factorial. Now on this one, I would take this series evaluated at n plus 1, so I'd get x to the n plus 1 divided by n plus 1 factorial, and then you divide that by a sub n, so that would be x to the n over n factorial, and then when you divide, you invert and multiply, so we'll flip this over and we'll be multiplying by n factorial over x to the n, and then we know that n plus 1 factorial can be written as n plus 1 times n factorial, and so the n factorials here cancel, and then x to the n plus 1 is the same as x to the n times x, so therefore we can cancel the x to the n's, and then we just have x over n plus 1. So we want to take the limit of that as n goes to infinity, and we can actually factor out the absolute value of x outside there, and since n is a positive number, we know the absolute value of 1 over n plus 1 is just 1 over n plus 1, so we don't need the absolute value there. And finally, we know that the limit of 1 over n plus 1 as n goes to infinity is 0, so if we take the absolute value of x times 0, we just get 0. Therefore, this limit is less than 1 for all values of x, and so since the radius here is r is less than 1 for all values of x, then the interval of convergence would be -infinity to infinity, and the radius of convergence is actually infinity. Okay, so I'm just going to summarize this one. I'm going to do the same thing I did on the previous problem. I take the limit of the n plus 1th term here divided by the nth term, and then that means I can flip the nth term over and multiply. And then here, you know that we really don't need the -1 to the n's here because we're taking the absolute value. So plus or minus 1, the absolute value would just be 1. So we can just eliminate those. And then we know that we can write x to the n plus 1 as x to the n times x. So we can cancel the x to the n's. And so here we just have xn over n plus 1. And if you factor the absolute value of x out and then take the limit of the n over n plus 1, that limit is 1. And so the absolute value of x times 1 would be x. And so the power series converges when the absolute value of x is less than 1, which would be from -1 to 1. And then we have to test at the endpoints. And so if you let x be -1, then this series actually becomes -1 to the n minus 1 times -1 to the n over n, which is -1 to the 2n minus 1. And actually you can show that that is simply negative the series 1 over n. So I'll leave you to do that, but it's not hard to show. Okay, and so that is actually a divergent harmonic series, so that series diverges. Now, if x equals 1, you actually just get -1 to the n minus 1 over n, and this alternating series converges by the alternating series test, so therefore the interval of convergence, it does not converge at -1, but it does converge at 1, so therefore we put the bracket with 1. And the radius of convergence is 1. And then there's a practice. There's actually a practice problem that you can do there below it. Now I'll finish this up with this theorem: convergence of a power series. If the power series converges for x equals c, where c is not equal to 0, then it actually converges absolutely for all x where absolute value of x is less than c. And if the series diverges at x equal d, then it must diverge for all x where absolute value of x is greater than d. And so I'll finish this section on the next video now.